Okay, this is the second in the series on the Wheelwork of Nature on vibration, frequency and discharge form. In the first part there were two video experiments where we used this equipment that we've got set up in front of us, although there are some changes here, to demonstrate the fractal Fern discharge. And throughout those experiments we saw that there was a very strong correlation between the frequency of the coil, of the secondary coil, and the nature of the discharge, so the form of the discharge. And we did quite a few variations in that experiment. Modifications to the power supply output, the tubes that we were using, tuning differences, all of those kinds of variations which didn't make really any difference to the form of the discharge. It was still the fractal Fern discharge, and we've considered that in considerable detail in the first part of the series. So in this experiment we are going to have a look at that discharge form when we compare it across a number of different secondary coils. So here we can see in the picture, here's the experimental setup. We've got 5 secondary coils. They are nominally all the same. They're constructed in the same way, on the same aspect ratio, same dimensions, same materials. The only variation is the fundamental series resonant frequency, and that has been affected by using different wire gauge. So the one here, this is the original coil. Its fundamental series resonant frequency is around 3.5 megacycles, and that's 155 turns on the coil. The next one over here, I've lined them up here so you can see how they look. That's nominally a 2 megacycle coil, so it has its fundamental resonant frequency at 2 megacycles. The next one down, this one is 1 megacycle. The next one is nominally 640 kilocycles, and the one at the end is 410 kilocycles. And these are the measured fundamental series resonant frequency. For a coil coupled with a primary, I go into a lot of detail on the website about the various modes, the upper and lower parallel resonant modes, and the central series resonant mode. And the frequencies I'm referring to now are measured using the standard measurement technique that I use, using the VNWA, the DG8 SAQ vector network analyzer. And each of these coils has been designed to, as the wire length and the wire gauge has been designed to give us a range of frequencies going from 3.5 megacycles all the way down to 410 kilocycles. Obviously the parallel modes will have frequencies either side of that. So for example, the original coil used in the first experiment in the Wheelwork of Nature, that's got a lower parallel mode at around about 2.7 megacycles and an upper mode starting around about 3.2 to 3.3 megacycles. And by using the vacuum variable tuning capacitor we've got here, we are able to shift the range of those frequencies as we did in the variations on the second experiment that we previously did. Now I've changed, so what we're going to do is we're going to measure those coils and we're going to look at the form of the discharge. For the lower frequency, for this experiment, I will use the first 3 or 4 coils. The difficulty with using a VTTC arrangement or vacuum tube Tesla coil arrangement with the lower frequency is because they have harmonics spaced. Well, the lowest frequency will have harmonics. It will have the fundamental at 410, that's actually measured, and then it's going to have the second harmonic above that at around about 750, and third harmonic above that around about 1 to 1.1 megacycle. And with the typical type of parallel loading capacitor that we use in parallel with the primary coil, that is usually around about 1 to 2 nanofarads. And for the lower frequency coils, that means they tend to resonate at the second or third harmonic rather than at the fundamental. To resonate it at the fundamental means we have to put more loading capacitance on. So for the parallel modes at the balanced point, for the lowest coil, that would need almost 12 nanofarads, and for this one it would need almost 5 nanofarads of parallel capacitance in the primary coil, which puts a significant load. This is a simple power supply circuit, and it was deliberately kept simple. I'll go through the setup again in a minute. It was deliberately kept simple in order to not add complications into the interpretation of what was causing the fractal Fern discharge. So for example, this is all run CW. There's no staccato control or pulsing control included in this. I mean, we will use that at another time, but I want to keep the experiment at this stage as simple as possible. The higher parallel capacitances for the lower coils, to try to make them resonate at their fundamental resonant frequency, puts a considerable load, capacitive load, at the anode end of the vacuum tubes, and that makes it quite difficult to make it oscillate at those low frequencies. Normally you would use a driven vacuum tube arrangement, so rather you would drive it from a frequency source with a preamplifier directly. That preamplifier, vacuum tube preamplifier stage would then just be driving the power stage, either directly in parallel or in push-pull arrangement. And we will be doing that as another experiment, and then we can actually run at the fundamental resonant frequencies of the 2 lower coils. Now, many people in the field make vacuum tube Tesla coils in this simple arrangement, and most of those you find will be resonating at the second or third harmonic. So somewhere around about 750 to 1 megacycle, sometimes 1 to 1.5 megacycles. So we will use here the first 3 or 4 of these coils. The lowest frequency coil I will leave for when we actually drive it directly, using a generator with a preamplifier stage and the power and then the final power output stage. That gives us a much finer control of frequency, allows us to drive the tubes directly at the frequency we want, and that means that we can drive it at the fundamental resonant frequency, the lower and upper parallel modes, in the way that this is connected. So the setup is these units form the tube power supply series. I have write-ups of both of these units on the website already. This is the tube power supply, the plate, high voltage and plate supply. We're using it as we did before in the first Wheelwork of Nature experiments, where the 2 series transformers are connected through a bridge rectifier. There is the normal blocking capacitor on the back, which is a 25 kilovolt, 25 nanofarad blocking capacitor to protect from high frequency reflected power going back into the power supply and damaging the semiconductors and other components in the power supply. Instead of using the single GU5B, we're going to use the dual 833C tube board. The reason we're going to do that, I did use that in the variations experiment, the last one that I did, and it has a more flexible range. So the two tubes together in parallel will oscillate over a wider frequency range than the single GU5B. So it means that in adjusting frequency we can take it down a bit lower and a bit higher. Also, their power handling, because they're in parallel, we get slightly more power handling out of those. We can easily push those tubes up to 3.5 kilowatts of power. So those are mounted on the part of the tube series heater, grids and screen units. They're already powered up, so two 833Cs in parallel. It's 10 volts, 10 amps each, so 20 amps is drawn by the heater supply. The setup, so this part is not being used. The GU5B and its associated power, heater control and the grid bias control is not being used in this experiment. We're just using the coil, the variable frequency adjusts through the vacuum variable capacitor, and the grid bias is on the side here for the 833Cs. So altogether that makes a Class C Armstrong oscillator. Very straightforward way of driving a Tesla coil. It's standard. And that was how I wanted it to be in this Wheelwork of Nature series, so that we see that we can start looking at where these discharge types and these properties and the phenomena that we see, we can start to get an idea or work towards where they're coming from, what is causing it. Otherwise it's so easy to become trapped in the idea that it's special pulse power supplies, the tubes are configured in a special way, it's a coil which is wrapped with a special geometry or with some kind of golden ratio type geometry, and I wanted to move that aside, just have a basic Tesla coil design for all the coils. As I said before, they are based on the same geometry, same components, just different wire gauge. There is the addition here of the feedback coil. In the first series I used the feedback coil which is underneath here. It's basically 3 or 4 turns of wire, but with the different range of coils here, then I need to be able to adjust with more control the number of turns. And this is a variable feedback coil. I will bring the camera in a little bit and show how that works in a minute. The secondary coil I have arranged so that it is easily removable. In other words, we haven't got to disassemble all of this in order to change for another coil, and I'll show how that works in a minute. We have the normal measurement equipment set up. Let me just pan the camera around. So we're doing the normal kinds of measurements with oscilloscope, frequency measurement, and also we have a high frequency Tektronix current probe there as well if you want to look at the envelope of the drive signal in more detail. So normal measurement equipment that I use. Once again, this era of measurement equipment is very good because it doesn't go haywire when you run Tesla coils at high power, which is a very common feature of more modern test equipment. As soon as you've got very high ambient electric and magnetic fields of induction, many measurement systems go crazy, or the software crashes, or they reboot. But these era equipment built on metal chassis, very well screened and grounded, and they continue to operate very well in the background of even running Tesla coils up to 3-4 kilowatts. So that's the measurement arrangement. We come back to here. So overall, in this experiment, I'm looking for a transition of the form and nature of the discharge from the Fractal Fern discharge to something else, based upon one of the things that we're going to change predominantly is the characteristics based on frequency, because each of these coils has a different frequency characteristic. Although, as I talked about in the previous write-up, the first in the Wheelwork of Nature series, for me that frequency is just a scalar measurement which is indicating that underneath there is a vibration, there is a relationship between the dielectric and magnetic fields of induction which is unknown to us at this moment, or at least in this experiment, what that relationship is and how that relationship changes with the qualities of the different coils and hence their fundamental resonant frequency. So it's those qualities of vibration that I am particularly interested in experimenting and finding out more. Okay, so I think that covers the experimental setup, the measurement equipment. I'm going to move the camera in a little bit closer to here so we can have a look at how this is arranged. And then we'll start the experiment. I will start it from where we left off previously, so I will just run this setup as it is. There, this is the original coil from the Wheelwork of Nature Part 1, and we will look at for each coil, the upper and lower parallel resonant modes. We'll do the frequency adjustments, and then we'll look at in detail at the nature and the form of the discharge. Okay, so this is a close-up now of the primary coil, the base of the secondary coil, and also the feedback coil here. Now the feedback coil is arranged so it feeds into the side here in the two connectors. It can easily be disconnected with these 2mm banana style connectors, and that actually feeds down under here out of the terminals at the other end and into the 833C tube board. And this coil is arranged so that it has tap points. So it is a coil wrapped on a plastic arranged former, and it has tapping points starting at the bottom. There I've numbered the number of turns. So the first one is 4 all the way up to 13. So I can adjust the feedback going to the grid leakage circuit, or the grid bias circuit, simply by where I put the tapping in. As the frequency goes down, I'm going to need to increase the feedback. That's up at turn 12. The current coil runs well at 6 turns with the dual 833Cs. They are fairly large tubes, so they need quite a reasonable amount of feedback. When I was with the GU5B, we were using only 3 to 4 turns, and that's also, the coil is now, because it's at the end here, it's now off axis, so it's not directly underneath, it's to the side, so that also usually involves an extra turn or 2. Let's move that away slightly. The secondary coil is arranged so that here is the base of the coil coming out, and that is also arranged on a 2mm. So I can simply remove the terminal, then I can bring a thin spanner underneath and rotate that. The secondary coil, it's all mounted with with nylon screws. Rotate that and lift it away, and there we can see at the base there it has the 2mm socket which connects the lower end of the coil down to RF ground, and it's tapped into the end here, and there is a nylon screw coming out of here, and then I completely take the coil away and change it for another one. So that makes it very easy to change the coil, which is what we need when we've got 5 coils to work with. Just take the spanner out and then plug the connector back in and reposition the feedback coil. So that's how that works. Now on the other side we have the inputs here. This is the 2 inputs for the vacuum, the KP14 Russian vacuum variable capacitor. It's variable from 20 to 1000 picofarads. That can be disconnected from the system by simply taking out and plugging into the nylon plastic top. So those connect it in to the circuit. The primary I'm using a different primary here as well. This is 12 AWG microstranded silicon coated wire, 7.5 turns, wound around a open plastic former at the back. I found that especially running at high power, the primary from the previous experiment, which was actually wrapped on a perspex, a clear perspex tube, it got too hot. So this is much better. The gauge of the wire is bigger than it was before, and also it has air. It has room for convection cooling with airflow going up through the back of the coil, which was before just down to the plastic. So that's much improved. We can run quite well sustained for periods at high power, up to 4 kilowatts. So those are the 2 connections for the primary, and then we have space here. Obviously there will be there's the input from the high tension, but also we have space there to put loading capacitors. And let me show an example of the loading capacitor. So this is this is a 1 nanofarad Russian 15 kVAR 4 kilovolt, normally 4 kilovolt capacitor. Into those we can connect sockets, leads, and they just goes down onto the bridge like that. So we can quickly add a range of different loading capacitors. There is a 4.7 nanofarad, and we also have a 2 nanofarad 6 kilovolt, and we use those as loading capacitors for the various different coils that we're going to run. The first 2, we only need to introduce this loading capacitor for coil number 3 at 1 megacycle. For the first 2 coils, the 3.5 megacycle and the 2 megacycle coil, we can tune those to their fundamental mode just using the vacuum variable capacitor. I will put the details of the specific details of the secondary coils and their design into the write-up, and I will also do the normal vector network analyzer analysis of these coils, so all the frequency and the harmonics will be very clear. for anyone that's interested in replicating this experiment. So that's all the details of the experiment and what we're going to do. So I'm going to first of all pull the camera back, and we'll just do a quick run just to show how things are working and look at where it was, where we left off from the last experiments in the last series. And then we'll get in, I will bring the camera in close to the discharge like I did before, and we start having a look at the characteristics. Okay, so I've pulled the camera back to the position where we can see all of the experiments. It's a little bit more noisy. I've turned on the cooling fans for here, and I've also turned on one of the cooling fans for the pair of transformers. And we're just going to run, this is now exactly the same position that we were in at the last of the variation experiments from the previous experimental run. So I'm just going to turn the lights down, and then we just do a straightforward run. Just check that's coming out on the camera. Yeah. So currently we have the 3.5 megacycle coil, and it is tuned to an optimal point at the lower parallel resonant frequency at around about 2.7 megacycles, and I will check that on the oscilloscope and on the frequency counter when we get started. So I will turn on the power supply, normal thing using the remote control. We can see the emergence there. I'm going to check the oscilloscope. It's 2.71 megacycles, confirmed also by the frequency counter as well. We're running at about, that's just at 600 watts. Just optimise, just check the grid bias. Yeah, we're on about the optimal position. We're on 6 feedback turns, so we just bring the power up. That's 2 kilowatts, running at 2.7 megacycles. .5 kilowatts, 3 kilowatts. It's a large fractal Fern discharge, up to 30 centimetres in length. Okay, good. Okay, so that is where we left off the experiment at the end of the last variations. I'm now going to move the camera in close like I did before, so we can look at the form of the discharge. Okay, so I've moved the camera in to a close position so we can have a look at the discharge. I will reset the camera to the same position for each of the coils. We're still running with a 3.5 megacycle coil. Everything is tuned as before, so we're just going to have a close-up look at that discharge now. I'll just check the frequency of oscillation, 2.71 megacycles. Look for the emergence. 400 watts. It's 1 kilowatt. Fractal Ferns starting to develop quite well. It's 1.7, 1.8 kilowatts. So fully developed fractal Fern discharge. 2.71 megacycles, 1.85 kilowatts. 2 kilowatts. Just take it up further as well. 3 kilowatts. Large, very strong, very bright. It tends to melt the copper probe at the top there, so I'll back it off a little bit. Keep it at about 2 kilowatts. Sustainable. So 2.71 megacycles. So I'm going to now drop the frequency. I'll just bring back the power down a little bit, down to about a kilowatt whilst I lower the frequency. 2.6. 2.5. We wind up again. 1.6 kilowatts. Obviously we've moved further away from the fundamental series resonant frequency, so the discharge is smaller. 2.5 megacycles. Fractal Fern, still well developed at 1.8 kilowatts. I'll take it down a little bit further, see if I can back it down a bit more. Starting to get difficult. 2.4 megacycles. 1.5 kilowatts, we're far from resonance, so we're having to push it hard. We'll take it back up again. 2.5. 1.25 kilowatts, 2.7. 2.8. Starting to get close to the series mode, to the transition between the lower parallel mode and the upper parallel mode. Nice clean waveform, sinusoidal, 2.8 megacycles. We'll wind it back down and we're going to flip over to the upper. So keep reducing the capacitance. Now we're running at 2.9 megacycles. We have flipped over to the upper parallel mode. Fractal Fern discharge all of the time. That's at 1.4 kilowatts. Obviously it's smaller and it's tighter. It's tighter and more compact. The arcs are smaller, tendrils are smaller, but it's the whole Fractal Fern on a smaller scale. Go up a bit more in frequency, getting quite far from the series mode. Still a nice oscillation sinusoidal. That's 3 megacycles. Fractal Fern still very much there. 2.5 kilowatts. Take it up a bit further. We might have to adjust the grid bias a little bit. Back it off, back the tubes off a little bit. Still got the Fractal Fern. That's at 3.1 megacycles. At 1.8 kilowatts. Okay, so I'm going to wind it back down a bit to its optimum points. That's the optimum point in the upper parallel mode. 3 megacycles. Nice tight Fractal Fern, that's 1.6 kilowatts in. 2.9798 megacycles. Nice tight fractal turn. We just adjust grid bias a little bit. Optimise that. 2 kilowatts at the upper parallel resonant mode. Drop that down. We're going to take it, transition it over to the lower mode. 2.7. There we are. Back down to the lower parallel mode. That's 2.75 actually. Drop it a little bit further. I'm just increasing the variable capacitance slightly on the primary circuit to do that tuning. 2.7. 2 kilowatts of power. Fractal Fern, both at the upper and lower parallel resonant frequencies. I'm just going to wind that down, turn off for the moment. Been running constantly up at around 2 to 2.5 kilowatts. So I'm just going to allow that to cool slightly. No real problem for the 833Cs. The anodes plates are not even glowing red. Fantastic pair of tubes they are. You really can push an awful lot of welly through those. So, just to summarise, we were able to go down as far as 2.4 megacycles, and we were able to go up as far as 3.2 megacycles. Going further than that, we start to get further away from the fundamental series resonant frequency. Bear in mind that the 3.5 megacycle coil is for the secondary when it's unloaded. When you add the primary there, then you will automatically see some loading on that. It's automatically going to shift, and you're going to get the lower and upper frequencies, parallel mode frequencies, depending on the loading capacitor, parallel loading capacitor that you put into the primary circuit. And that is how we're adjusting frequency here. It's a nice simple way of being able to vary the frequency over a reasonable band. We were able to go to 2.4 to 3.2 megacycles, and we had the fractal Fern discharge over that entire frequency range. So most developed at the lower parallel resonant mode, and when we're pushing up to 3 kilowatts, that's about a 30 centimetre high fractal Fern discharge, and the strength of the streamers, in other words hot white streamers, there's a lot of, that power supply push a lot of current into that. That's a great advantage of the microwave oven transformers, which the plate supply is based upon, is they really can push a lot of current into that, so you get those hot white streamers, which makes the discharge very well defined. Then we moved up to the upper parallel mode, and there we saw the whole fractal Fern discharge was still present, but tighter, smaller. The arcs were smaller, but still had the same basic form across that frequency range for the vibrational properties of this secondary coil. Okay, so what I'm going to do is I'm going to change the coil. What I'll do, I think, is I will pull the camera out slightly so we can see the coil being changed for the first time, and see how that works. Okay, so I pulled the camera back out again at the region around the coils, and I'm going to swap the 3.5 megacycle coil for the 2 megacycle coil. That's the one that I've just put into the picture. So I'm going to do the same procedure before. I've of course checked that the HT is off and isolated before doing this. I'm going to unwind this coil. That can go down. I'm going to put the 2 megacycle coil in. Re-plug in. I'm going to leave the feedback coil the same. I may need to increase that up to 8 turns, but I'll see how it performs first of all. I'm going to take the top electrode, plug that into the other coil. And then we got to retune. So at the moment the vacuum variable capacitor will be up at around about 180 no, more than that, probably about 220, 230 picofarads. I'm going to increase that now up to somewhere around about 570, 600. So I'll just set it at a lower point. I can actually measure it to set our starting position. Connection. Right, 660. So I shall set it a bit less than that, say round about 600 picofarads as a starting point for the tuning. Okay, so I've changed the coil. It was all very quick. I will put that up to 8 turns to start with, and then I shall reposition the camera now so we can have a look at how the discharge looks. Okay, so I've repositioned the camera. We have the 2 megacycle coil on there, so that's going to have an upper parallel mode at around about 2.2 to 2.3 megacycles, and a lower parallel mode at around about 1.7 to 1.8 megacycles. So currently we are set to the upper parallel mode, and if we now start that up, we'll have a look at what the frequency is. Okay, so we just ignited there, just measure the frequency. So there we are, 2.3 megacycles on the upper parallel mode. 400 watts, and we're going to wind up the 8 turns. On the feedback coil is about right, it's nice and smooth. Just going to adjust the grid bias, that seems to be an optimal position. So we wind up, and up at, that's 2 kilowatts, 2.27 megacycles, Fractal Fern discharge. Still the Fractal Fern. Nice and stable. CW 2.45. Wind it down about 2 kilowatts we're running that at. Nice clean waveform on the oscilloscope, 2.3 megacycles. Let's go up a little bit, let's wind down the power a little bit, go up in frequency, becoming more compact, 1.5 kilowatts, that's 2.4 megacycles. Go up a bit more, obviously falling off now for the same power as we're going further away from the series fundamental mode. That is now 2.5. 1.7 kilowatts. And about almost 7 kilowatts out. Fractal Fern still. Still the Fractal Fern at 2.5 kilowatts. Okay, we're going to wind down a bit. Kilowatts, 2.35. Go back down a little bit more. 2.25. 2 kilowatts. Still the Fractal Fern. Let's go down a little bit more. 2.19. Almost 2.2. 1.8 kilowatts. Wind it down a little bit further. There's coming towards the transition between the upper and lower parallel modes. What you could hear is the instability on the tubes. That is now flipped over 1.8. Get it a little bit more stable. There we are. So we're not right on the transition. We are 1.73. And we have also, the discharge port is now swords. It's not the Fractal Fern anymore. Let's go down a little bit further. Tune it a little bit. 1.7 at 1.3 kilowatts. I'm just going to make an adjustment to the plates are starting to glow red a bit, so I'm going to actually increase the feedback a bit. They're having to work quite hard. I'm going to go right up to 12. We'll have a look and see how that performs. Yes, it's better. 1.6. Still a slight curve. So we are running at 1.7. 1.7 megacycles. Still a little bit of a curve, but it is no longer a Fractal Fern discharge. It is what is commonly known as the swords discharge, which is very, very common for the vacuum tube Tesla coil. It's what almost everybody sees. The majority of people see when they experiment with VTCs. That's 1.9 kilowatts, 1.7 megacycles. So we're going to go down a bit from there. Just wind it down a little bit. .6. Swords now straighter, more up the centre. 1.6 megacycles. Let's go down a bit more. 1.55. 2.8 kilowatts. Straightening out. The swords, the discharge, the Fractal Fern discharge is now gone. It has now straightened out into the swords. There are still very, very small secondary streamers, but they are really now just primary streamers emanating from the source point. 2 kilowatts. 1.6 megacycles. Plates are glowing, not too much. Well within the dissipation of the 833Cs. We go down further in frequency, 1.5, 1.7 kilowatts. We are getting further and further away, of course. Let's go down quite a bit more. 1.5, 1.6 kilowatts. Quite a far from tune now. But they're still straight. They are not fractals anymore. They're not the Fractal Fern discharge. 1.5 megacycles. Okay, I'm just going to take it up a little bit and give it a rest for a moment. Back it back down to only 400 watts. 1.6 megacycles. The optimum. It's about the lower, that's 1.78. Let's put it down to about 1.7. 2.7, there we are. Power again, plates are called 2.3 kilowatts. Swords with a little bit more curve. If we look at the outer ends of the discharge, we can see there's slightly more curve. We are heading towards the fractal Fern, but we're not there yet. 1.73 megacycles. That is the optimum tune for the lower parallel resonant mode. I'm just going to stop and see if I can back off the feedback to the coil and still get a good Fern or a good discharge. So that will, if I back off the feedback a bit, it will reduce the amount of power pulled. So switch on again, down to 1.9 kilowatts. I'm just going to, that was 10 feedback turns. I'm going to go down to 8. We turn that on again. Visibly small, 1.6, and they are visibly smaller. So about 10. About 10 feedback turns was about the optimum balance between the length of the discharge and the amount of power pulled. Okay, that's 10 to 1.9 kilowatts. 1.72 megacycles. That's about the optimum point for this coil for the lower parallel resonant mode. So I'm going to switch over now. I'm going to just reduce its power whilst it switches over to the upper parallel resonant mode. So keep reducing the capacitance. 1.75. Almost 1.78. Starting to come unstable. Transition between the lower and upper parallel mode. That's the transition point. Fractal Fern starting to come back. Now we're stably into the upper parallel mode, 2.2. And as we turn the power up, we may have to put more feedback on here. I'm going to up there to 12 turns of feedback. Pushing it too hard, I'll back it down to 8. Good. 1.3 kilowatts, 2.2 megacycles. Fractal Fern. 2.3 kilowatts, 2.23 megacycles. Up a bit in frequency, becoming tighter, more tight curves. That's almost 2.4, 2.38. Even further. Back the power off a little bit, down to 2 kilowatts, 2.45 megacycles. Fractal Fern, still developed. .5 megacycles. 2.7 kilowatts. We're quite far away from the resonant point. Not going to run it too long there. Back down. 2.3. That's stable. 2.35 Fractal Fern discharge. There we go. 2.23. That's about the optimum point for the upper parallel mode. 1.5 is up there to 2 kilowatts, 2 kilowatts, 2.23 megacycles. Fractal Fern's well developed. I'm going to keep on, just going to bring the power down to about 1 kilowatt. Keep going down in frequency. 2.12, starting to get close to the transition between the parallel and the upper and lower mode. There it's now in the lower mode, 1.7. It's flipped over from 2.1 to almost 1.8. And the fractal Fern has gone. 1 kilowatt. Go down a little bit further in frequency. Get to the optimum point. Power 2 kilowatts, 1.7 megacycles, 1.7. Fractal Fern is gone and now in swords. Back to that point we were at before. Plates are glowing red, not excessively. We're at 2 kilowatts. We could probably adjust the feedback up again, up to 10 turns from 8. Yeah. 2 kilowatts. That's about the optimum point. Swords with a slight curve. Very, very common discharge form for a relatively small but powerful Tesla coil. Just going to back the camera off a little bit so that one can see the rest of the experiment going on. Also we can see the tubes, we can see the glow on the tubes. Let's give another perspective, let's turn that back on. It's 2.3 kilowatts. You can see the glow on the 833Cs. Perfectly happy within there. They are force cooled, air cooling, coming up the tubes. 1.7 megacycles. .3 kilowatts. Up it a bit more. 3 kilowatts. Swords almost 30 centimeters high. Nice glow on the plates. 3.1 kilowatts. CW. 1.7 megacycles. Okay. Bring it back down. 2 kilowatts. 1.3, 2, 1 kilowatt. See the plate starting to cool down a little bit. 1.7 megacycles. And off. We just let the system cool down a little bit. We'll just check the temperature of the primary. Yeah, that new primary is so much better. It's high temperature silicone coated wire, and it is hot, but it's not affecting the structure, whereas before it was making the tube soft. Good. Okay, so if we just summarise for this coil, so we were able to take this coil really between about 1.5 megacycles all the way up to about 2.4. And the interesting one here is that we saw at the upper parallel resonant mode we had the well-developed fractal Fern discharge, but when we flipped over to the lower mode it's basically swords. The fractal Fern discharge had gone. The swords are straightened out, and we don't have that richness of detail where we have secondary and tertiary streamers coming off of the main ones, all the very small filaments. There is a very different type of discharge, and that was between the upper and the lower parallel modes. And the waveforms in that were quite clean, so they were mainly sinusoidal and with some harmonic detail as well. So the drive is very straightforward, and over that frequency range we're able to transition from the Fractal Fern discharge at the upper parallel mode down to swords at the lower. Okay, good. What we're going to do, and that's the 2 megacycle, that's normally the 2 megacycle coil. So now I'm going to move down to the 1 megacycle coil, and we're going to take a look at the form of discharge. Now I'm just going to change the coil. I've showed you how the changing of the coil works. I'm going to put the camera back by the discharge, close to the discharge, and then we'll have a look at normally the 1 megacycle coil. Okay, so I've now fitted the 1 megacycle coil, put the camera back in the same place. I've also fitted the 1 nanofarad loading capacitor as I showed earlier in the video. So we've now got a range of variable capacitance between 1 nanofarad and 2 nanofarad. The optimum point here, the balance point, is about 1.5 nanofarad, and I have tuned it first of all to the upper parallel mode, the optimum position for the upper parallel mode. I've put the feedback coil up to 12 turns to give a good amount of feedback to the 833Cs, and now we'll give that a run. So I'll just turn on. Here we go, just check the frequency. 1.35 megacycles. 1.3 kilowatts. Again, swords. Not the Fractal Fern discharge, but swords. Up in power, 2.5 kilowatts, 2 kilowatts at 1.35 megacycles. Straight swords. Very, very typical for this kind of coil at this kind of frequency. We'll go up a bit higher in frequency. We're moving away from its series mode, 1.35 megacycles, 1.4 megacycles. Up some more, at 2 kilowatts. 1.5 megacycles. Swords. It's all only swords here. We don't have any of the Fractal Fern. Going back down, going closer to the fundamental series mode, 1.35, and a bit further, 1.31 power. 3 kilowatts, very hot, glowing red, 3.3 kilowatts, 30 centimeters. Back down to 2. 1.34 megacycles. I will just try going to less feedback if I can. I'll put it down to 8. See if... No, that's not enough to oscillate. I just tried to oscillate then, it wasn't enough. Got to go back up to 12. That's it. 2 kilowatts. 1.34 megacycles. Okay, so we keep winding down. Just drop the power a little bit first. 1.3, 2.4 kilowatts, much the same structure. transition point, you can hear the instability. 1.26 megacycles. Keep going down. 1.23. Just going to tune the bias, grid bias slightly. See if we can clean that up a bit. 1.25, we're at the lower parallel mode. Quite small, hard to get it to oscillate here. The tubes are having to work quite hard. 1.3 kilowatts, as we can see it's quite a small discharge. That's 1.24 megacycles. Just at the transition point. If I go down further, try and see if I can get it to oscillate there. 1.1 megacycle. Tubes are having to push hard, it's far from resonance. Very small discharge now. 970 kilocycles. 1 kilowatt. 1.7. Tiny discharge. Going up in frequency again. 1.2. Up in frequency, getting back closer to its resonant point. At the transition between the upper and the lower. Now we're just in the beginning of the upper parallel mode. Very stable there, that's its best operating point, 1.8 kilowatts. .26 megacycles, 2 kilowatts. Swords, very straight, hardly any curvature. Very few well-developed secondary streamers. Mainly they all just emanate directly from the source point at the end of the copper probe. Kilowatts, stable CW, 1.26 megacycles. Good. Okay. Just again give the tubes a chance to cool down a little and the primary coil. So there we went from 970 kilocycles all the way up to around about 1.4 megacycles. Again, it's all swords. We were able to go through the transition between the lower and the upper. More difficult to get this coil to resonate at its lower parallel mode. The impedance of the coil will be getting quite high at the lower parallel mode. What with the parallel capacitance value as well, the lower parallel mode impedance will now be quite high in relation to the plate resistance. The plate impedance, total plate impedance of the tubes, combined tubes. So therefore the power transfer from the tubes to the coil is progressively becoming poor. And this is where it becomes harder and harder now to... Let me just adjust that slightly. This is where it becomes harder and harder to resonate a VTTC at the lower and lower frequencies, because the loading from the primary circuit and the impedance of the secondary circuit becomes difficult to start. The match starts to become further and further away from the vacuum tubes. This is where we would move over. For the 4th and 5th coil, we would move over to using directly driving with a signal generator and a vacuum tube preamplifier stage, which would then drive the 833C power tubes. We will do that in a subsequent experiment, and we'll also push it. We'll also drive it in push-pull with that arrangement. But overall, now I'm going to move the camera back and we'll just look at the overall conclusions from this experiment. Okay, so in summary so far, we've run the first 3 of these coils, the 3.5 megacycle, the 2 megacycle and the 1 megacycle coil, and we've seen a transition in the second coil, the 2 megacycle one, between the upper parallel mode and the lower parallel mode. It moved from the Fractal Fern discharge to a sword-like discharge, which, as I said before, is very common for a standard VTTC around about this frequency. Many of the vacuum tube Tesla coils you see built and operated online, they are running around between the 1 and 1.5 megacycles, and what we see here is very characteristic of those type of results. So we ran here from about 970 kilocycles up to about 3.4 megacycles, and we've seen that transition, which is related to frequency and, more importantly, vibration, and I suspect also the relationship between the dielectric and the magnetic fields of induction is what's giving us that change of discharge form. Okay, good. Well, I will put more of the details into the write-up of the coils, their design, some pictures as well of the close-up pictures of the setup, and then that really is the third experiment in the second part of the Wheelwork of Nature: vibration, frequency and discharge form. Great.